a short video on the concept of Silico Mycelium Symbiosis. So, if you don't know, silicon represents the computer and mycelium represents the wiry network of the fungus. Some people refer to the fungus as the internet underneath our feet, or some people say the wood wide web, because we now understand that mycelia really connects species to one another. In this picture you can see how trees via their roots actually communicate with one another via the via a fungal species. So it's not just plants communicating with one another, mycelia also communicate with something like nitrogen fixating bacteria and other bacteria, and is really part of big symbiotic processes happening within the earth. If we zoom in on the mycelium network, we see that mycelia is really just a connection network of hyphae where we have branch points and also join-up points. And in our project, we are really interested in the external liquid environment surrounding the hyphae edges, because it's in this environment where the symbiotic interaction takes place. Symbiosis at its core is a process of chemical exchange. So what effectively happens is the fungus interacts with another symbiont. It might be the roots of a plant, it might be a bacteria, and the deal is all about I give you some chemical and you give me some chemical, and we do the exchange transaction via the intracellular space here given in blue. So our project is about replacing the symbiont with an algorithm or even artificial intelligence so that we can have a computer communicating to a fungus. And this might sound like a very good idea because we intend to do the communication via the intracellular space, but one might ask, how will you do this? So if you want to hook the computer and make it communicate with the fungus, the first thing you need to do is to measure what is happening in the intracellular space. Because if we can define the concentrations, or we can measure the concentrations in the space, we can now take those measurements and we can feed it to the algorithm. Whatever the algorithm is, the algorithm will decide on an action, and the action will now communicate to the pumping of chemicals. So effectively, we'll pump at a decided rate sets of chemicals into the intracellular space. Okay. We might also be interested in removing chemicals from the space, because we talked about the space being an exchange space of chemicals. So for that, we can use pumps to dilute, really just pushing through water at a faster rate, the intracellular space. And effectively, what we're doing is we are controlling the concentration space. We even have an example in our lab. We work with the fungus Rhizopus oryzae, and what you can see here is the fungus immobilized on a pipe in a bioreactor. So the extracellular space now becomes a bioreactor, and you can see here's the concentration of the liquid that we talk about. We circulate the liquid in here to measure what's in the liquid, and then we link that measurements to a computer so that we can decide what to add or remove chemical wise from the mixture. This is perhaps a better presentation of our bioreactor. So we start by making measurements. In our example, we will measure the pH, we will measure the dissolved oxygen, we will also measure the off-gas from the system, and we take oxygen and CO2 measured, and based on that we get a lot of information on what the organism is doing. We now feed this to a computer and we get back, by controlling our feed rates of nitrogen, oxygen, and the carbon source. In addition, if we want to remove metabolites from the intracellular space or the bioreactor, we can just wash water through the system at a faster rate to effectively remove the unwanted chemicals from the system. So all of life is but one big chemical reaction, and we can quantify the chemical reaction that takes place as the fungus reacts in the bioreactor. We can, in real time, because our measurements have to be very quick, measure the oxygen off gas, we can measure the CO2 off gas, we can measure the pH drop caused by fumarate excretion, and then in addition we have balances. We have carbon, hydrogen, oxygen, nitrogen balances, and given all of this, we can fully quantify the real-time metabolic response. And I'm just going to add this because the important part is for the computer to be able to communicate back to the organism. We need to be fast in our measurements so that we can be fast in our responses. That is something that we already do in the lab. So in a sense, we are creating a new type of organism where our algorithms, whether they're artificial intelligence, whether they're driven by our own decisions, are interacting with the fungus in real time. Okay, our case, the objective will be to maximize fumarate excretion, but that's besides the point. The important factor here is that we're using a metabolic response and a control of the concentration space to effectively communicate with the fungus in real time. There you have it, Silico Mycelium Symbiosis, or SMS, in a nutshell. The application that we're working on is in a bioprocessing environment, but of course the concept is far bigger than just bioprocessing. We're providing a unique new angle to study fungal physiology, also to gain better understanding in terms of how symbiosis works in nature. And from a bigger perspective, it's all about getting taught by the fungus in terms of how chemical sustainability works. The list will go on, and we are inviting you to join this exciting SMS project so that you can add to the list. Thank you very much.